So what if the central body is not a black hole? For example, what if it's, I said that inside a black hole there is something called a singularity. It's a place where gravity becomes infinitely strong and really weird in its properties. And the laws of general relativity get replaced, presumably by something called the laws of quantum gravity. It's conventional wisdom that singularities today exist only inside black holes, but what if you had a naked singularity? Well, here is a particular naked singularity in here, and an orbit of a small object, say a small black hole, going around that naked singularity. And the orbit is not at all like what we saw before. It's chaotic. It sort of has little jumps and jiggles. And it is chaotic in the mathematical sense of chaos, and quite remarkable. And obviously, the map that you would manage to extract from this, if you can extract the map, will be wildly different. So we have the possibility to search for naked singularities. This is one example of weird things that might be done. I'm particularly interested in the dynamics of the space-time geometry around colliding black holes, and we explore this by computer simulations, and then we compare the shapes of the waves that are come off in our simulations with what is seen by LIGO and Virgo in order to see whether or not this dynamics of warped space-time that we are predicting is correct. And we get very good agreements between the predicted wave shapes and what is observed. And so we believe that the true warping of space is what is predicted by the computer simulations. So this is a simulation showing the warping of space around then two black holes that are spiraling together. Each black hole is like a funnel in terms of the warping of space. The color coding is the slowing of time. I have to tell for the mathematicians and physicists, there's a slight cheat here. What we have is a two-dimensional surface in the orbital plane of the two black holes. Any two-dimensional surface can be embedded in a three-dimensional flat space. So that's what's being done here. The bulk that you're looking in from is a three-dimensional flat space. But that embedding can only be done locally. And so if you try to do it and you go around the black hole and you come back, the shape does not match up smoothly. And so there has been a kludge done here. I won't tell you what the kludge is, but there's been a kludge done here. But you can still take this seriously as representing, in some fairly accurate sense, the warping of space around the black holes as they collide. Now we're going to slow the movie down as the collision begins. You see there's a huge splash in the shape of space forming, like the splashing of the surface of the ocean in a giant storm at sea. And the color coding is the slowing of time. It oscillates wildly, settles down, and the gravitational waves go away. So this is what we call geometrodynamics, the dynamics of the highly warped space-time around two colliding black holes. And we've been learning about this from computer simulations. And particularly interesting, but I won't take the time to describe it, is what we have learned about how these vortices that stick out of black holes behave when the black holes collide. I want to wind up gravitational waves by briefly saying that one of the thing that I think is going to be most interesting with gravitational waves in the coming few decades is to observe the birth of the universe and the birth of the fundamental forces that govern the universe. As an example, when the universe was a trillionth of a second old, the electromagnetic force and the weak force came apart, gaining their own identities in what is called the electroweak phase transition. And so inside this bubble, if this was as it could have been what's called a first-order phase transition, inside of this bubble, the electromagnetic force exists. Outside, it does not exist. And in here, it exists. Outside, it doesn't exist. The electromagnetic force was born. There was no such a thing as electromagnetic force before then. And these bubbles then are predicted to expand very fast and collide, producing a burst of gravitational waves. As the universe subsequently expands, those gravitational waves are shifted to longer wavelengths, and today they're in LISA's frequency domain. So with LISA, we hope to see the gravitational waves from the birth of the electromagnetic force when the universe was very young. We expect to see gravitational waves from the Big Bang. I'm going to go through this very quickly because I want to wind up with a few words about time travel and wormholes. But the basic idea is that something came off the Big Bang, and whatever it was, in terms of gravitational waves, was amplified by a process called inflation at the beginning of the universe that some of you are aware of. And these gravitational waves then, a very rich spectrum of gravitational waves that have then been amplified by inflation, they interact with a hot gas when the universe was about 380,000 years old, and they put this polarization pattern on the hot gas, which then astronomers have searched for. They have found this polarization pattern, but there is noise in the data, and they're not sure that whether what they've actually seen is due to the noise or whether it's really due to these primordial gravitational waves. That will get sorted out, I'm sure, within the next 10 years. And we then will have, today, we will have then indirectly, through this pattern of polarization on the sky, we will have then detailed information about the Big Bang singularity in which the universe was born, but mixed together with information about inflation, the very rapid early expansion of the universe, convolved together. I look forward eagerly to seeing this. There are predictions for what the result should be, and I expect the predictions will turn out to be wrong, and it will force the theoretical physicists to go back to the drawing boards. And then in the middle of this century, there is likely to be a successor to the LISA mission called the Big Bang Observer, which will see these primordial gravitational waves with periods, instead of hundreds of millions of years, periods of a few seconds, radically different periods. And again, just from past experience, I'd be surprised if the theorists have it right when they predict what is seen.